Today we're going to be talking about rational expressions, which is really just another word for an algebraic fraction. So the first thing I want you to be able to do is determine when a rational expression is undefined. To answer this problem, we are going to use the fact that we can't divide by zero. Division by zero is undefined. So when is the expression undefined is basically asking us, when does the denominator equal zero? So I set that denominator equal to 0, and now I have a quadratic equation. One side equals 0, so I'm going to go ahead and try to factor. I need a product of 6 and a sum of -5. -2 and -3 work. So I set the factors equal to 0, and when I solve, I get x equal 2 and x equal 3. These are two numbers that if you were to plug into this rational expression, you would get something that's undefined. Again, it's that fact we cannot divide by zero. Division by zero is undefined. Now, with the rest of this discussion, this video, we're going to be talking about how we can simplify and then multiply and divide rational expressions. So let's start with simplifying. These are basically fractions. To simplify, we're going to cancel out common factors. That word factor is actually really important here. That means we can only cancel things out if they're part of a product. So in this first example, I don't see any plus or minus signs. Everything is a product. The numerator is 2 times 3, that's the 6, x times y, and the denominator is 3 times 5 times y times y times y. I have a common factor of 3 and a common factor of y. If I cancel those out, I'm left with 2x squared over 5y squared. And that's my answer. Now, if you want to do this canceling in your head, that is perfectly fine. You do not need to write out the work that I have done here. But I wrote it out because I want to emphasize the difference between example A and example B. In example B, we have differences. I see subtraction. That means I cannot cancel things out until I have products. Because I have differences, to write this as a product, I have to use all of those factoring techniques that we talked about earlier. The numerator, x squared minus 3x, has a GCF. I can pull out an x, and I'm left with x minus 3. The denominator also has a GCF. We can take out a 2, and we're left with x minus 3. Now my common factor is x minus 3. I cancel those out, and I'm left with x over 2. One more simplification problem. Again, I see differences. I see subtraction, so I cannot do any canceling right now. I have to factor before I can do anything else. The numerator has a GCF of 5. If I pull that out, I'm left with x minus 4. Now the denominator is a negative x squared plus 16. I just switch the order of those terms. It's almost a difference of perfect squares. And there's a little trick I'm going to do here. Because there's a negative in front of the x squared, factoring's hard when there's a negative in front of the x squared. I'm going to factor the -1 out to change those signs. If I factor a -1 out of the denominator, now I'm left with a difference of perfect squares, x squared minus 16. The x squared minus 16 can be factored as x plus 4, x minus 4. If I cancel out the x minus 4's, I'm left with a 5 over -1 times x plus 4. I usually just put that negative in front of the fraction, but you could leave it in the denominator, or you could put it in the numerator. And so in blue is my final answer. Now, multiplying and dividing rational expressions is actually really similar to simplifying. We're going to be doing lots of factoring and canceling. But before we do that, I want to remind you how we multiply and divide with just regular fractions. When you multiply, you don't need an LCD. You can just multiply straight across. However, it's often easier if you try to simplify before you multiply. In this case, I have a common factor of 3 that I'm going to cancel out of the 3 and the 9. And I have a common factor of 4 that I can take out of the 4 and the 8. Now when I go straight across, I get 1/6. Division is really similar to multiplication with one small difference. To divide by a fraction, we multiply by the reciprocal. In other words, we copy down the first fraction, we change it to multiplication, and we flip the second fraction. Now we do the same thing. We look for common factors. In this case, there aren't any. And then we just multiply straight across. So 27 over 32 is my answer. So let's take a look at an example. In this first problem, I don't see any addition or subtraction. That tells me that everything is already a product. And so I can just start canceling things out. I can start looking for common factors. There's a common factor of 3 in the 3 and the 9. There's a common factor of 2 that can be divided out of the 2 and the 4. And finally, there's a common factor of a that we can cancel out of the top and the bottom. To finish, I just multiply straight across, just writing down what's left. So in the numerator, the only thing that's left is the a times b, and in the denominator, we have a 2 times 3, or 6 left. And there's my final answer. Now this problem is a little bit different than my next example. Part B, n squared minus n over n squared minus 1 times n squared over n plus 1. Now I see those plus and minus signs. That tells me as soon as I see addition and subtraction, that tells me I cannot do any canceling yet. Instead, I need to get this into a product. I need to factor. So the numerator of the first fraction has a GCF of n. If I pull out the n, I'm left with n minus 1. The denominator of the first fraction, n squared minus 1, is a difference of perfect squares, n plus 1, n minus 1. There's no factoring I can do with the other fraction, I just wrote it down. Now I look for those common factors. There's only one common factor, the n minus 1. So if I multiply straight across, n times n squared is n cubed, n plus 1 times n plus 1, I'm just going to write that as n plus 1 squared. There's no need to go any further with these problems. You can always leave your answers in factored form. All right, one more multiplication example. In this problem, we've got a lot of factoring to do. Again, those plus and minus signs are what's telling me I have to do some factoring. So I'm going to just break this down into 4 separate problems. I start with the numerator of the first fraction, x cubed plus 27. No GCF, 2 terms. This fits into that pattern, sum of 2 cubes. Because 27 is 3 cubed, I'll be plugging x in for a, 3 in for b, into my cube formula. So in factored form, I've got x plus 3, x squared minus 3x plus 9. Okay, denominator of the first fraction, 2x squared minus 3x plus 1. No GCF, 3 terms. I'm going to use the AC method. 2 times 1 is 2, so I need a product of 2 and a sum of negative 3. Negative 2 and negative 1 will work. Copy down the first term. I break the middle term up into 2 terms using those numbers, negative 2x minus 1x. Copy down the last term. I can take a 2x out of the first 2 terms, left with an x minus 1. I pull a negative 1 out of the second 2, left with an x minus 1. So in factored form, we've got x minus 1, 2x minus 1. Numerator of the second fraction, 4x squared minus 1. No GCF, 2 terms. This is a difference of perfect squares. I'm going to factor this as 2x plus 1, 2x minus 1. And finally, denominator of the second fraction is just x plus 3. There's no factoring we can do there. So finally, I rewrite the entire problem in its factored form, and I look for common factors. There are 2 common factors here, the x plus 3 and the 2x minus 1. I cancel those out, and then I write down what's left over. And that's it. I don't actually have to multiply these out. You can always leave your answers in factored form. So my answer is x squared minus 3x plus 9 times 2x plus 1 all over x minus 1. All right, finally, let's get a division problem in. Before I do anything else, I am going to copy down the first, change to multiplication, flip the second. Some people learn this as copy dot flip. We're basically multiplying by the reciprocal. So I rewrite the problem as a product, flipping the second fraction. I also decided where I had the 9 minus n squared to write that as a minus 9 squared plus 9. I find it helpful to put the variable first. It makes the factoring a little easier for me. So numerator of the first fraction, mn, can't be factored. It's already a product, no plus signs. But the denominator, that minus n squared plus 9, if I factor out a negative 1, that turns into an n squared minus 9. And now I have a difference of perfect squares, n plus 3, n minus 3, with that GCF of negative 1 in front. Numerator of the second fraction, n squared minus 3n, has a GCF of n. If I pull out the n, I'm left with n minus 3. So finally, I rewrite the entire problem in its factored form, and then I look for common factors. I can cancel out the n minus 3's, and I can also cancel an m out of the top and the bottom, leaving me with an m squared on the bottom. Finally, I multiply straight across, leaving my answer in factored form. That negative 1 that was left over, I'm just going to write that as a negative sign in front of the problem. And then the numerator, n times n is n squared. And then in the denominator, we have an m squared times n plus 3. And that's it. That's my final answer. So to summarize, when you're simplifying, multiplying, or dividing, the concept is really the same. You have to factor these things before you can cancel. The idea is you can only cancel out products, and that's why you have to factor. So the theme of this section is make sure you factor everything as much as possible before you do anything else. Hope this makes sense. If not, feel free to send me an email or drop by my office.